Hello, my name is Boian Mitov, the president of Mitov Software, and in this session I will show you controlling Visuino programmed Arduino robots from Delphi applications. There are many different types of Arduino-based robots, such as smart cars, walking robots, self-balancing robots, robots with manipulators, and even drones. The robots will typically have some input sensors and output devices such as LEDs, speakers, motors, and actuators. The robots will usually have some form of communication, and finally, they all typically have some kind of control board, usually Arduino based, but it can be based on other controller, also being able to be programmed from the Arduino IDE. Here are a few examples of mostly Arduino-based robots. As you can see, they come in all kinds of shapes and sizes, and some of them may have even manipulators. And as in this case, even remotely controlled video camera. Some of them may be flexible in terms of being able to connect the different sensors in different ways with jumper cables, as in those two human technology robots. Others, like this LA-Go robot here, are designed to be used predominantly with fixed number of sensors and configurations, allowing you to focus mostly on the programming part. There are also some walking robots, like this LA-Go penguin bot, and not all of the robots necessarily are Arduino based, as is the case with this, in this case, ESP32 based robot, but originally this robot was designed for microbit, and I have replaced the microbit controller with this microbit connector compatible ESP32 board. Here is example of another LA-Go product, in this case a self-balancing robot that I recently received and will use in this session to demonstrate the access to some of the sensors. As you can see, the robots typically will have sensors, motors, in some cases servos, controlling a variety of parts, and they will have LEDs that can be used to display status, speakers, and typically some form of communication, as is the case of this Bluetooth LE module on this robot, the Wi-Fi and Bluetooth LE within the ESP32 of this one, or the optional Bluetooth Classic that can be connected to this robot. Now let's go ahead and start experimenting with some of the robots. The first task when we work with a robot typically is to check that our sensors are working and we can read from them. For this, we will start with one of the smart cars. Start a new Visuino project, add shield, select the correct shield type, in my case version 2 with remapped wires, and add the shield by clicking on this button. When the shield is added, the functionality of the shield and the robot will be shown on the Arduino component. We can test the ultrasonic ranger. Connect the output of the ultrasonic ranger to the input of the serial port Connect the USB cable to the robot so we can program the Arduino board. And click on this button to generate the Arduino code and open the Arduino IDE. Make sure that Arduino Genuino Uno is selected as board and select the COM port where the Arduino is connected. Click on this button to compile and upload the code. Now we can switch to the serial port, select the COM port where the Arduino is connected and connect the COM port. You will see the distance of the ultrasonic ranger displayed in the terminal. And changing as I am placing obstacle at front of the robot. We can see the same in the scope. Now let's try to make Delphi application to connect to the robot and monitor the ultrasonic ranger. Start a new Delphi application. Add a COM port component. The component is part of the communication lab which you can download for free from the Mitov website. The library is free for non-commercial purposes and you can experiment with it as much as you want. Add a terminal component, also part of the same library. Switch to the OpenWire view, connect the output of the COM port to the terminal, click on this button, and select the COM port where is our robot. Compile and run. You can see the values from the ultrasonic ranger arriving in our terminal. And you can see that they're changing if we point the robot in different directions or place obstacle in front of it. This application was very easy to make, however there are few issues. We can read only one sensor and the data arrives in text format. This format is good to display in something like text terminal, but it is difficult to handle the data in scopes, plotting components, gauges, or anything else. Visuino and Communication Lab in Delphi include components that can help us send multiple values between the Arduino and the Delphi application. There are two sets of components, packet and structure. Packet is typically used when you work with serial communication, as in our case. Serial communication can often have interruption of the stream, and the stream can be somewhat unreliable. This means that we will need to use packet functionality to detect the beginning of the packet and check for packet integrity. When we work with sockets, structure is a better choice since the sockets ensure the integrity of the stream. We will start with new Visuino project to test this functionality. For this, we will use a different robot. This self-balancing robot has accelerometer and gyroscope module on it. Obviously, before we start even balancing the robot, we have to learn how to read the data from the module and how to work with the data and interpret it in a meaningful way. I will start by connecting the robot with USB to the computer so I can program it. Since this is Arduino robot, we don't need to change the board, but we will need to add the robot shield. In this case, LEGO balancing robot shield. As you can see, the shield added our accelerometer, gyroscope, and we have even temperature sensor which is built on the same module. For simplicity, I will read only the 3 values of the accelerometer. I will add a packet component and click on this button to open the Elements editor. There are many different types of elements that we can add. In this case, I want to send analog values, and I'll add 3 such elements. And close the editor. I'll click on the output of the accelerometer, move the mouse to the first element, and the rest will automatically spread to connect properly. Click here, and everything will be connected. Next, I need to make sure I have a unique header for my packet so I can detect the beginning of the packet. I will add some random value as example 5555. And I will connect the output of the packet component to the input of the serial port 0. Click on this button to generate the Arduino code and open the Arduino IDE. Make sure the Arduino Genuino Uno is selected as board and select the COM port where the robot is connected. Click on this button to compile and upload the code. The code is uploaded. Let's test this first in Visuino. Select the COM port in the serial communication and select packet 1 as format for our communication. As you can see, on the scope, immediately we have 3 channels, and we also have visual instrumentation. Let's connect and test the project. You can see the data arriving from the robot. And let's try rotating it around. You can see that the data changes as we rotate the robot around. And the same can be monitored on the gauges. Now let's try getting data inside Delphi application. Create a new project. For this, you can do VCL or FireMonkey project. Add COM port component. Add unpacked component. And add 3 gauges. In my case, 3 angular gauges. We can also add a scope component. Switch to the open wire view. Connect the COM port component to the unpacked. Add 3 binary floating point channels to the unpacked component. Add 2 more channels to the scope component as example by dragging this small button here. Connect the 3 elements to the 3 gauges and the 3 channels of the scope to the 3 unpacked channels. Make sure to add the same header marker, 5555 in my case. And finally, select the COM port where the Arduino is connected. Select the 3 gauges and change the min to -1 and the max to 1. Compile and run the application. You can see the data arriving and being displayed on the gauges and on the scope. Let's try to rotate the robot. you can see that the data arrives and is being properly displayed. In this project, we are displaying the acceleration in the X, Y, and Z direction. It would be nice if we can convert that acceleration into 3D orientation and control a 3D shape in FireMonkey application to show the orientation of the robot. For this, we'll need to convert the acceleration into degrees. We'll use acceleration to angle component to convert our acceleration. Disconnect the packet component. Connect the accelerometer to it. And connect the acceleration to angle component to the 3 packet elements. This will be the roll, pitch, and yaw converted in degrees. Click on this button to generate the Arduino code and open the Arduino IDE. Click on this button to compile and upload the code to the Arduino. The code is uploaded. Now it is time to create our Delphi application. Start a new multi-device application. Create a blank application. Add a viewport 3D. Add a round cube. Light and lighting source. I'll arrange my scene. And I will set the light material source. To control the rotation of the cube, I will add visual light binding to the X, Y, and Z rotation angle. I will add a COM port component and unpacked component. Switch to the open wire view. I will connect the COM port to the unpacked component, and I will add 3 floating point channels. I will connect the 3 channels to the X, Y, and Z properties of the cube. I will set the unique header marker that we set in the Visuino project. And I will select the COM port where my Arduino is connected. Compile and run the application. Now you can see that if I rotate the robot, the cube on the screen will follow the rotation. This is a good starting step when we start working with self-balancing robots. The noise that you see from the accelerometer can be reduced by using special filters in Visuino. They are often utilized in self-balancing robots. Unfortunately, in this short session, we will not be able to cover all of the details of programming self-balancing robot, but I hope to post more videos on this topic and full tutorials on how to program such robot. Now we will program a robot car to be controlled over Bluetooth from Android app. We will use the accelerometer on the Android device to control the robot by tilting the mobile device forward, backward, left and right. First, I will select the shield for my robot. For this example, a Lego robot V2 shield with remapped wiring. The data will arrive from the Bluetooth module over the serial channel. We will send 3 channels of data. To split them, we will use unpacked component. I will set the unique head marker at 3 analog channels. We will connect the input of the unpacked component to the output of the serial channel. We also would like to monitor the distance measured by the ultrasonic ranger and send it over the serial channel. So I will use the opportunity to connect the input of the serial channel to the output of the ultrasonic ranger. The accelerometer will send forward, backward, and left-right turn value. We will need to convert those to values of speed of the left and right motor. For this, we can use the steering differential component. I will add the component and I will connect the left and right channel to the 2 motors. The accelerometer will send values between -1 and 1. We will need to convert them to values between 0 and 1 to control the speed in direction. We would also like to have some insensitivity to make sure that when the phone is nearly horizontal, the robot will not move around. For this, we can use dead zone scaled component. We will drop 2 dead zone scaled mapping components and we will connect the first channel of the unpack to the first one, the output of the first one to the speed. This will control the speed of our motors. The second one to the input of the second remapping component and the output of the component to the direction pin of the steering. I will need to change the input mapping range. Instead of 0 to 1, -1 to 1. I will also set initial value on the input to 0. The project is ready. Click on this button to generate the Arduino code and open the Arduino IDE. Make sure that Arduino Genuino Uno is selected as board and select the COM port where the Arduino is connected. Click on this button to compile and upload the code. The code is uploaded. Now I can go ahead and disconnect the USB cable from the robot, and I can install the Bluetooth module. Please note that there are labels for the different pins on the module. This is VCC or positive power, ground, TX and RX. Their corresponding labels right here on the Arduino shield. Make sure that the power and ground are matching exactly the labels on the shield, otherwise you may burn the module. So as you can see, VCC is connected to +5 volts and ground to ground. The TX and RX pins are connected to the corresponding opposite type of pins, TX to RX and RX to TX. The robot is ready for us to control from the phone. We can power it on and it will be ready to be controlled. Now it is time to go ahead and create Android app using Delphi. I will start by creating new multi-device application in Delphi. I will select blank application. Since the application will use the tilt to control the robot, I will open the project options and the orientation. I will select landscape orientation. For Android user permissions, I will also enable the Bluetooth and Bluetooth admin so I can use the Bluetooth from inside the application. I will add 4 labels. For this label, I will set a text connecting. This label will show my distance. I will also make it slightly bigger so additional text can be displayed after the distance. I will add a trackbar. I will switch to the Android and I will set initial value of 50. I will set the enable of the trackbar to false. Now I will go ahead and add a switch. I will set enabled also to false. I will add a Bluetooth component. I will set it to enabled. I will switch to the code view and add a field into my form class. This field will contain the socket once we are connected with the Bluetooth device. I'll switch to the events. On discovery end, I will add the following code. Here, we will enumerate through all of the devices until we discover HC06 device, which is the name of our module. We will pair with the device if we discover it. We will enumerate the services. We will create a socket for the first service that we discover. And if we're successful, we will connect to the socket, enable the switch, enable the trackbar, and we will hide the label that shows connecting. However, if we fail to discover our device, we will set this discovery to false. We will use this discovery flag, which I will also add to my form, to keep searching for devices. I will switch back to design and I will add motion sensor. I will make it active by default and add packet component. To get the packet data, I will use generic filter. I will switch to the OpenWire view and I will connect the packet to the generic filter and we will add 3 floating point channels. I will also set the head marker to 55, 55, the same as we did in Visuino. We'll add a timer. We'll use this timer to handle our communication and to keep checking for the position of the motion sensor as well as whether or not we are connected properly to the Bluetooth device. I'll double click on the timer to generate the on-timer event. First, in the timer, if we have not discovered device yet, we'll set the in discovery to true and we will tell the Bluetooth to discover any devices within 5 seconds. What will happen is after 5 seconds, this event will be called with the list of all discovered devices, and if we fail to discover the device we are looking for, we'll set the in discovery to false again, and this code again will be executed, restarting the search. Next, we'll check if we have a motion sensor. If the motion sensor is present, we'll read the acceleration x and y and we'll display it as text in label 1 and 2 right here. Next, we will check if we already have created socket and if we are connected to the socket. We'll check if the switch is checked. We'll open the elements editor for the packet, and we will use this right-click and copy type name to copy the type of the elements. Since the component can have a variety of elements, we will need to pick the type that we have added. I will paste it, typecast the first element to floating point type, and call the setValue method, passing the acceleration. I will do the same for the second channel. This will control the motors. If the switch is not checked, I will set the value to neutral 0, so the car will stop. Finally, for the last element, I will set inverted value of the track bar. I am dividing the value of the track bar to the maximum in order to create values between 0 and 1. Finally, I will add some code to read data from the socket and convert it into text. I will use a temporary storage inside my class for the partially constructed text. So I will decode the text using UTF-8. I will keep adding it to the text. I will keep checking until I reach end of line. And then I will remove everything until the end of the line, collecting the characters into this last text. And if I have succeeded to extract new text, I will display the new distance in centimeters. I will need to add few local variables used in the code. Click on this button to compile, upload the code, and execute in debug mode on my smartphone. Initially, the app will show that the Bluetooth is connecting. It will take a while until it discovers and connects to the device, and once connected, we can use the track bar to control the orientation of the servo, with the ultrasonic ranger. Here we can also see the distance to the nearest object at front of the ultrasonic ranger. As example, in this case, the distance to my hand in centimeters. Occasionally, we'll have some errors in the measurement due to sound noise. If we turn on this switch, we can start controlling the robot by tilting the phone left, right, forward or back. We can stop the control by flipping the switch back. Now I will show you how you can use Animation Lab to animate robots with manipulators or legs. For this, we will use the Lego Penguin bot. I'll select the Penguin bot as board. It has two legs with two servos on each leg. One is for the hip and one for the foot. We will use the serial port to send data to control the legs. The data will be sent in the form of packet, and we will use unpacked component to split the channels. I will add unpacked component, and I will add 2 analog channels. I will connect the 2 channels to 2 servos for one of the legs. I will set a unique head marker. This can be any random number, in my case 5555. And I will connect the input pin of the unpack to the output pin of the serial channel 0. I will connect the USB cable to my Penguin boat, like this. And now I can go ahead and upload the code. Click on this button to generate the Arduino code and open the Arduino IDE. Make sure that Arduino Genuino Uno is selected as board and select the COM port where the robot is connected. Click on this button to compile and upload the code. The code is uploaded. Now I will create a Delphi application that will control the robot. I will start by creating Windows VCL application project. Add a timeline. The timeline is included in Animation Lab from Mitov software, and the library is free for non-commercial purposes. I will double-click on the component to open the timeline editor. Since we will animate 2 servos, I will add 2 single floating point channels. I will select the first channel, and I will add 2 cubic spline periods. I will select the first period, and I will add 3 points. I will select the first point and set a value of 1 for it. I will select the second point and set a value of 0.2. And for the third point, I will set a value of 0.5. I will select the second period and add 1 point in it. I will set a value of 0.5 for this point. I will select the second channel, and I will add 2 linear periods. For the ending value of the first period, I will set 1. Here we will have linear interpolation between 0 to 1, and then from 1 to 0. We can add as many periods as we want. I just want to make the project very simple, so you can create it in just a couple of minutes. Close the timeline editor. We don't want the timeline to start automatically, so I will set Enable to false. I will add a button. I will double-click on the button to generate the event. And in the event handler, type EL timeline 1 start. This will start our timeline. I will add a packet component and a COM port. I will double-click on the COM port and select the COM port where our robot is connected. Switch to the OpenWire view. Click on this button and add 2 floating point channels. Connect the output of the packet to the input of the COM port, and connect the 2 channels from the timeline to the inputs of the 2 elements of the packet component. Select the packet component and add the unique header marker, the same values that you use in your Visuino project, in my case 5555. Compile and run the project. flip the robot upside down so we can watch the movement of the leg. To make sure we have enough power to power both servos while controlling the robot, I will also turn on the power from the batteries. Click on the buttons. You will see that the leg followed exactly the movement of the two timeline channels. Every time I click on the button, you will see the leg performing the same movement. We can make much more complex animations, but this should give you a very good start, and it is something that you can try within just a couple of minutes. Now we will program ESP32-based robot for Wi-Fi remote control. We will start by selecting board type, BPI bit from Banana Pi. In order to control the robot over Wi-Fi, we'll need to expand modules Wi-Fi and add at least one access point to which the robot will connect. I will set this to my access point hotspot, and I will set the password. Close the access points editor. To make it easy to connect to the robot, we'll give it a DHCP name. I will call it robot. Next, we will add TCP/IP server socket. I will set a port as example 8080 and close the sockets editor. Now I will select the shield, or also called in the case of microbit carrier board of the robot. It will add the motors, ultrasonic ranger, LEDs, the buzzer, and everything else that is on this robot board. In this project, we will control the two motors and the LED RGB lights. We will control the motors with direction and speed that we will receive from the tilt of our mobile device. To convert into the differential speed of the two motors, we will use steering differential component. I will connect the component to the two motors. I will add dead zone scaled components. Two of them. I will connect the first one to the speed and the second one to the direction of the steering component. I will select the two components and set input range of -1 to 1 and initial value of 0. I will add a split structure component, and I will click on this button to add the channels. 2 analog channels and 1 color channel. I will connect the first analog channel to the first dead zone scaled component, the second one to the second scaled component, and the color channel to the lights. I will connect the input of split structure to the output pin of the socket. I will carefully connect the USB cable to the ESP32 control board on top of the carrier board of the robot. Now the robot is ready to be programmed. click on this button to generate the Arduino code and open the Arduino IDE. Make sure that in the board manager you have the ESP32 support added. Select ESP32 Dev module as development board. Select the COM port where our robot is connected. Click on this button to compile and upload the code. Once the code is uploaded, we can disconnect the USB port. And now I can power the robot and it will be ready to be controlled over Wi-Fi. Now we will create the Delphi app to control the robot over Wi-Fi. Start with File, New, Multi-Device Application Delphi. Select Blank Application and select the target as Android. Add 2 labels. I will add color picker. Add a switch. I will add motion sensor. And I will add timer where I will read the orientation of the motion sensor. I will read it 10 times a second and I will send the data over Wi-Fi. I will add make structure component and I will add a client socket to connect to the robot. I will set the name of the host. In my case, it is robot. And due to the type of DHCP registration, ESP32 requires a dot to be added at the end of the name. Set the port number. Enable the motion sensor. Switch to the open wire view. And connect the output of the make structure to the client socket. Click on this button to open the elements editor and add 2 floating point channels and 1 color channel. Close the editor. Switch to the code. Since the color picker provides alpha color and we will need normal color without alpha channel, I will need to write a small conversion function. Here we receive alpha color and we convert it to a normal RGB color. Double-click on the timer to generate the on-timer event. Here, first, we'll check if the motion sensor is available. If it is available, we'll set the text properties of the label 1 and 2 with the acceleration X and Y from the sensor. We'll check if the switch 1 is checked. Double-click on the make structure. As you can see, the different elements are of different types. It is simple to copy the name of each of the types, so I'll copy the name of the float 1 channel. I'll paste the type to convert the element 0 from the structure into floating point structure element type. And I'll set the value to the X value from the motion sensor. For channel 1 of the structure, I will set the value to acceleration Y. If the switch is off, we'll set the two values to 0 to stop the motors. Double-click again on the Make Structure component and copy the type name for the color channel and paste it in the code. For element 2 of the structure, we'll set the value to the converted value from the color picker component. Since we will use the tilt of the phone to control the speed and the direction of the robot, we'll open the project options, and for the application orientation, enable custom orientation and select landscape with home left. Make sure your Android device is connected to the USB port. Click on this button to compile, upload the code and run it in debug mode on the device. Here you can see the angle of the two accelerometers displayed in the labels. I can change the colors of the LEDs from the color picker, and if I turn on the switch, I can start driving the robot. By tilting the device left and right, forward and backward. If the device is horizontal, the robot will stop. And if I switch off the switch, the tilt control will be turned off. Thank you for watching the session. Once again, my name is Boian Mitov, the president of Mitov Software, and here are some of the Mitov software products. VideoLab, a video processing library, AudioLab, audio processing library, SignalLab, digital signal processing library, VisionLab, computer vision library, PlotLab, data visualization library, InstrumentLab, visual instrumentation library, IntelligenceLab, artificial intelligence library, LogicLab, Boolean logic library, AnimationLab, Universal Animation Library, Communication Lab, Serial and TCP Communication Library, Control Lab, Industrial Control Library, Visual Line Binding, Universal Visual Line Binding Library, Mitov Runtime, a free Delphi library, OpenWire Studio, a graphical development environment for Windows, Visuino, a graphical development environment for Arduino, Visuino Pro, a graphical development environment for Arduino-based industrial PLC controllers. Mitov Software also maintains some open source libraries such as the OpenWire library and iGDI+, a Delphi-friendly GDI+ library.